Hello, ladies and gentlemen. Mr. Dorfler back at you with another daily dose of Dorfler. Once I get my intro all smoothed out and finalized, I won't have these little hiccups right before I start. Anyway, here we are on the last section of notes for Chapter 5, but not only for Chapter 5, but for the entire semester. Okay, and it's going to be a short set of notes and a short homework assignment. Now, if you haven't checked Planebook, I have changed up a few things the other day, and we are going to have a quiz over sections 3 and 4 tomorrow. So, or whenever the next class period is, depending on when you watch this. Anyway, excuse me. So make sure you check Planebook, stay on top of everything like that, so you know what's coming on. Now, our final section of the chapter talks about power. Okay, and in power, we are going to talk about the concepts of energy, time, and power and how they relate. We're going to calculate power in 2 different ways and explain the effect of machines on work and power. We're actually not going to do that. We're mostly focusing on, the different ways we can calculate power. So, power can be solved in one of 2 ways. First of all, power itself is the quantity that measures the rate at which work is done or energy is transformed. And so we can get the first formula that you need to write down is P is equal to W divided by delta T, meaning power is equal to work divided by the amount of time it takes to do said job. Now, in power's calculations, the SI unit for power is watt, okay? That's basically joules per second. So make sure whenever you answer your questions for power that you answer it in terms of watts, all right? There's another formula that we can and will use, and that is how we can incorporate force and speed. And that is power is equal to force times speed. Pretty difficult, huh? And so really, that still gives us power in terms of watts, because it's Newton times meters divided by seconds, which is Newton meters per second, which Newton meter is a joule, and per second. So there you go. They're the same thing. Now, that's all a really easy breakdown, because if you think about it, work itself, okay, to calculate for work, you have force times distance or displacement of the object. So if you were to substitute the equation for work into W right here, you're going to get force times distance or displacement divided by time, which then again, distance or displacement divided by time is speed. So that's where we get the breakdown for this equation here. So we're going to hop right into a couple of examples here. I've actually added a second example after this one for you to pay attention to and help solve. So anyway, first off, we have a 193 kilogram curtain needs to be raised 7.5 meters at a constant speed in as close to 5 seconds as possible. The power ratings for 3 motors are listed as 1.0 kilowatt, 3.5 kilowatts, and 5.5 kilowatts. Which motor is best for the job? Well, let's see what we know. Okay, let me get out of here and let me get into my other camera here. And let's dim the lights ever so slightly. Okay, so we know that we have a mass. Come on, camera. Come on, camera. That'll be working. Okay. Excuse me. So we know we have mass at 193 kilograms. We know that we need to do it in as close to 5.0 seconds as possible, and it needs to travel a distance of 7.5 meters. We need to figure out the best power for this particular job. Okay, so what we need to do is we're going to solve just for power, okay? And whatever the power rating is for these parameters that we require, we're going to compare it to the 3 motors that we have available to us that were mentioned in the problem, okay? So power is equal to work divided by total time But remember, this is going to be force times distance over delta t, but we're not told what the force is directly, but what we do know is the mass, and we also know what gravity is. So it's going to be mgd over delta t, okay? And so we're going to get power is equal to the mass, 193 kilograms, multiplied by 9.81 meters per second squared, multiplied by the distance of 7.5 meters that it has to be raised, divided by the time of 5 seconds that this needs to be done. So when you multiply those through and divide by 5, you are going to get an overall power output of 2.8 times 10 to the third watts, or if you put it into kilowatts, 2.8 kilowatts. So we need to figure out which one of these motors would best fit. Okay? Well, again, the total power output that is required is about 2.8 kilowatts. If we are underpowered, it will take far too long for this task to be completed. If we have far too large or far too powerful of an engine, it's going to be too fast. So, we have a 1 kilowatt, a 3.5 kilowatt, and a 5.5 kilowatt. Well, the 1.0 kilowatt, it's underpowered. It's actually less than the power that is required for this particular job. So that's out. The 5.5 kilowatt is enough power, but it seems to be almost double what is required. So the best motor for this situation to meet all this criteria would be the 3.5 kilowatt motor. It's only slightly more powerful than the required power for this situation. And so that would be the optimal motor for this curtain raising. Okay? Next, excuse me, here we have the engines of the Queen Mary. This is the new one, okay? That could deliver 174 megawatts to propel the massive ship. How long does it take for the engines to do 7.31 times 10 to the 10th joules of work on the ship? Okay, so again, let's write what we know. We know that we have a total power of 174 megawatts, which is really 174 times 10 to the 6th watts. We know that the amount of work done is 7.31 times 10 to the 10th joules. We need to figure out how long it's going to take for this to happen. And so using the equation, P equals work divided by delta T, solving for delta T, we get work divided by power. And so we can then start plugging in our values here. Our work values is 7.31 times 10 to the 10th joules divided by 174 times 10 to the 6th watts. Yes, I understand the 174 times 10 to the 6th watts is not necessarily the most correct scientific notation, but we're just basing it off of the prefix of mega, which is times 10, it's 10 to the 6th, blah, blah, blah. Okay. So when we calculate all of this, we end up getting an answer of 4.20 times 10 to the second seconds. Well, that's quite a bit. So we can convert seconds to minutes, taking this value, and it ends up being approximately 7 minutes to complete that much work with that much power. Okay? So there you have it. A couple basic calculations for you regarding power. Now, what I want you to do now for your homework is I want you to do questions 3, 4, and 5 under practice F on page 181, as well as questions 1 and 2 underneath section review, also found on 181. Again, the homework you are to do is questions 3, 4, and 5 on the practice F on page 181, as well as questions 1 and 2 underneath the section review, also on page 181. Okay? So there you have it, folks. That is your last discussion for the semester. We made it halfway through the year so far. Anyway, I'm going to call an end to this video, and also going to post the assignment submittal post in a separate post to this video. So keep an eye out for that. But I will see you all later on. Bye-bye.